So now I'm going to go into the first unit for the, and so this is stuff you would have covered in AP Environmental Science A. So you would have covered it in the fall. Okay. So this is where I'm going to try and go as quickly as possible to try and answer as many of these questions as possible before the hour is up. So this answer is anthropogenic. So a man-made product is also known as anthropogenic. Okay. There we go. Define the term ecological footprint. Okay, now I'm just going to type this for you. It's basically the amount of productive biological land and water needed to supply a population with all its resources and dispose of waste. Okay. And then what I can do is I can put this this PowerPoint under like the user links section of the course. I'll put a link to it. That way you guys can use it almost like flashcards, and then you'll have this video as a key, basically. Okay, sketch or label the following on the world map. Okay, the equator. I'm going to try my best to draw a straight line. I'm not really doing an excellent job of drawing a straight line. So that should be the equator. Let's see, what else do we need to draw? We need to draw the Mediterranean Sea. Here. So we have the Mediterranean Sea. What's next? The Ogallala Aquifer. This is Ogallala Aquifer. Okay, so the star is right in the middle of the O. The island of Mauritius. Let's see. It's right here. This island is endangered because of rising sea levels. Let me see if I can put this a little closer to the island. Okay, and that's also where the Dodo used to live. Saudi Arabia is right here. Questions like this always take so long. Indonesia. This little like that kind of area, that's Indonesia. Okay, Philippines. That's going to be right about here. Philippines are right here. Panama is over the other side. This is where the Panama Canal is located. Iceland. Right here. And California is over here. We know California. They like to list California because that's where supposedly Fremont is located, and that's where a lot of the FRQs are talk about. Okay, so a positive feedback loop. This again is something that you would have done in your environmental science A course. So global warming is a type of positive feedback loop, and this means basically, so we have melting ice, right? That increases black surfaces, which then increases albedo, which then encourages more global warming, which then increases black surfaces, which then increases the albedo, which then, you know, on and on and on and on. So that's what they consider a positive feedback loop. Negative feedback loop. So this one, let's say we have water temperature increases evaporation, which then puts more moisture in the air. Which then forms clouds, which then reflects more rays, which then warms the atmosphere more. Okay. So there's that. Okay, 3 examples of organic compounds. Now these are just examples, so there's obviously lots of other ones. Or basically organic is anything that is carbon based. So for example, like methane, right, is CH4. So that's carbon based. We have hydrocarbons. Obviously they're carbon based, so they're called carbon, right? Glucose. Right, glucose is C6H12O6. Inorganic things are things that are not carbon based, except for carbon dioxide is kind of sometimes considered inorganic. That's kind of a bad example. Instead of that, you could say like sulfuric acid. And then the third one could be like ammonia. I think this one, sulfuric acid is, I know that one's H2SO4. Nitric acid is like HNOX. I don't remember exactly what the number is. And then ammonia is NH3 or 4. I don't remember which one. One is ammonia and one is ammonium. Okay, so now if we want to talk about the different these different what am I trying to say? Compounds, what can we say about them? So carbon is basically in all living things. That's why, like, if you notice, like, sometimes, like, there's a, like, if you talk about, like they talk about aliens will say, like, carbon-based life forms in movies sometimes. That's what that is. The largest reservoir of carbon is a rock. It can be all phases. So solid, liquid, or gas. And the cycle duration is long. Nitrogen is in proteins, like in DNA, things like that, and also plants need nitrogen a lot. Uh-oh. The biggest reservoir of nitrogen is the atmosphere. I don't really like this rocks. Let's say more like living things, like ocean, trees, things like that. Rocks, I don't know. I'm not really thrilled with that rocks. This was a worksheet that like someone else made, and I didn't really like it. For nitrogen, we don't have a lot of real natural methods of transport, but the cycle is short. Okay, let's see the next one. Phosphorus. Phosphorus. See, this is why I didn't like rocks, because phosphorus is really more stored in rocks. In fact, phosphorus is the only cycle that doesn't have an air portion. There's no atmospheric component for the phosphorus. Phosphorus is in ATP. It's in our bones. It's our teeth. And it transports through erosion. Which I guess nitrogen can be transported through erosion too, so we could write that if we wanted. And producers. And then the last one is water, which I know water is not really an element, but we're just going to go with it. Is a solvent. You need it to live. The largest reservoir is the ocean, and then it's transported through evaporation, runoff, all that sort of things, and it's a short cycle as well. Okay, so there is our little chart. Okay, so the balanced equation for photosynthesis. I would memorize this. And if you memorize one of them, like if you memorize the photosynthesis equation, you automatically have the respiration equation. So, because they're just backwards of one another. So at least that is a benefit. So we have 6 carbon dioxide plus 6 water plus sun equals C6H12O6. Remember I talked about this earlier? So that's glucose. So it makes sugar basically, and which is the food, and oxygen, which is what we breathe. So that's the equation for photosynthesis. And now the equation for cellular respiration is the opposite. So we have C6H12O6 plus oxygen, right? That's why we breathe oxygen. The cellular respiration is what happens in, well, people think that cellular respiration only happens in animals and photosynthesis happens in plants, but that's not really true. Cellular respiration happens in everyone, and photosynthesis just happens in plants. So photosynthesis, plants will use photosynthesis, right? And then they will, to make the food, and then they'll use cellular respiration to turn the food into energy so they can use it. So that's kind of a misnomer that some people think that just plants use, or just animals use cellular respiration, but that's not really true. Okay, so now this is a math one. So you'll have to do math for this. So this one says, if the grass is on 100 hectare of grassland, grow at an average rate of 1 centimeter a day, the average volume of grass that's added to the grassland each day is blank meters cubed. And then it says the density of the grasses that grow in the grassland averages 400 kilograms per meters cubed. The net primary productivity is approximately how much? Okay, so the first thing we have to do is find the average volume added to the area each day. So we have to turn the hectares into meters squared. Okay, so I wish I'm gonna try and do it with my little pencil thing. It's not working today. So I'm gonna try and do this. No, I want to do. I'm gonna write it because I don't know. It just seems like math goes better if you write it. So we have 100 hectares, and I'm just gonna call them H's. So I don't have to write the whole thing. And it's times 10,000 meters cubed. So there's 10,000 meters. Meters squared. There's 10,000 meters squared in 1 hectare. So basically, we're just converting right now the hectares to meters. So let me get like 1,000,000 meters squared. Literally a million. I wish I had my pen. It looks so silly to write like this. Well, I have my pen, and it works on the other screens. It just doesn't work in the PowerPoints right now for some reason. Meter squared. And then we need to multiply this by 1 centimeter. So 1 centimeter is 0.01 or 001 meters a day. So then we'll have 10,000. So we'll have kind of what we started with. It's kind of funny. And all your answers will be kind of like this. Since you can't use calculators, your answers will be the math will be relatively easy. That's a good thing about not allowing calculators is your answers. They usually give you pretty like decently easy numbers to work with. So then we're going to take that 10,000 meters. So that answer goes right there. And then we're going to take that 10,000 meters cubed and we're going to figure out the net primary productivity. Okay, so you see we have 10,000 meters cubed per day, and then we need to multiply that by this 400 kilograms, so this should be kilograms. This is going to allow us to get rid of our meters cubed. Get rid of this, get rid of this. Then we'll have we'll have 402. This is so tedious with the another pencil. I might do the next one without just typing it. And we'll have that. Sorry, I made a mistake. Okay. Sorry, I'm like, what is this? Okay, we need to, so I was going to do it in multiple steps, but in the key that I'd made, I went ahead and did it in one step. So I'm just going to follow that so I don't make any more mistakes. So I was going to do this and then I was going to do the next step, but anyway, I'll just do it all at once. So now we got rid of our meters cubed, right? So now we just need to get rid of our kilograms. So I was going to do that later, but I'll go ahead and do it now. So we have 1,000 grams in 1 kilogram. Because the answer asks for it in grams. So then we have for, I'm gonna write this in scientific notation, so I'm going to write all those zeros. Times 8 to the 9 grams per day. And then we need to multiply that by our 1,000,000. Sorry, we're going to divide it by our 1,000,000. So we'll do, I'm just going to do like nothing on the top, or like 1, and then like 1 e to the 6. Does that make sense to y'all what I'm doing here? So that's going to give me 4,000. Grams meter squared day. Okay, now I'm going to write this in words because the next part's easy. So I'm going to do 4,000 grams per meter squared per day. I'm going to multiply that by 365 days in 1 year. And I'm going to get this number. So we did 4,000 grams per meter squared per day. I know you guys don't see this until I like release it. So this allowed us to cross off the days. So then we ended up with grams meter squared year. So that's what we did by doing that. Let's go to the next one. I just wasted a whole bunch of time on that one. So which I really didn't want to do. So, okay, let's see. So I'm going to write this. Evapotranspiration means that water is moved from the land to the atmosphere with plants serving as an intermediary. So the big point of this is that it recycles water. Okay. Next. Okay, phew, another section. Okay, biodiversity, fragile ecosystems. Okay, so what are some biotic things? Biotics are things that are living. Okay, so you're going to have animals, you can have plants, you can have bacteria. And biotic is basically anything that's not alive. So they use soil as an example. I'm not sure how I like soil, because soil has like, living things in it. So let's say dirt. Since soil, we usually think of the living things in the soil as well. So let's not call it soil. Okay, so now we're going to match the following. So these are all different sort of animals that are living. So let's see. Zebra mussel is an invasive species. A Galapagos tortoise is endemic to the Galapagos Islands. The American alligator is a keystone species in its ecosystem. The salamander is an indicator species. Most amphibians, or most indicator species, are amphibians. So that's a good, if you didn't know these, salamander is an amphibian, so that's probably an indicator species. The Norway rat is a generalist. It tended to spread the plague. And the giant panda is a specialist because all it eats is food. Define the term biodiversity, and this is just the variety of species. Okay. This is like a weak statement that they want you to make less weak. Protecting the endangered species like the giant panda costs too much and should be stopped. So you might want to say something like protecting the giant panda diverts resources from critical areas and should no longer occur. So those critical areas, and you could list something like, say, healthcare, you know, whatever you want. So those critical areas can continue to receive the funding they need. You know, something like that. Okay, here we go. A Pacific yew is a tree. Specifically, it's a conifer tree. And it is endangered because it's used to make a drug for breast and lung cancer. A piping plover is a bird, and it is endangered because coastal areas used for nesting are being developed by humans, but I'm not going to type the humans part. An orangutan is an ape, and it is endangered because rainforest, which is its habitat, has been ruined due to deforestation. The dodo was also a bird, and it is extinct because it was a delicacy. Delicacy and was flightless, so unable to escape. Onward and upward. Okay. So an ecosystem component, an economically valuable service that it provides. So each critter, we're going to say something useful that this thing does. A honeybee pollinates, right? That's pretty useful. The water cycle, what does it do that is useful? It purifies water naturally. A forest purifies air. It also acts as a carbon sink. And it decreases erosion. So I guess we put more than one for the forest, but that's okay. A bat eats mosquitoes, which are dicky, and they spread diseases. It can actually help with pollination and seed dispersal. Bacteria can break down waste and can also be used in photosynthesis. A coral reef is a habitat. And protect coasts from storms. A wetland can filter water. It can protect from storms. It can also serve as a habitat for birds and nursery for fish. So maybe that was more than we needed, but that's okay. So whaling is justified in the name of science by the countries of Norway, Iceland, and a bonus country, Japan. Next. Okay, populations. Okay, so for this, we're going to draw a line that represents linear growth, and then we're going to draw a line that represents exponential growth. So I'm going to do my best to draw straight lines. Okay, something like this. This would be any linear, so I'm going to put L. It's something that kind of goes up like that. It curves up. This would be considered exponential. So I'm going to put E. The 4 most populated countries in the world. China, India, here we are, and Indonesia. I bet you guys didn't think we were going to be at the top, huh? An equation for the rule of 70. We basically do 70 divided by R. And this is going to give you the doubling time. And R equals the growth rate. Okay, so now we're going to use that equation. Okay, so a city has a population of 50,000 in 2012. If the population of the city grows at an annual rate of 2%, in which year will the population reach 100,000? Okay, so this is our doubling time, right? So what we're going to do is, in order to do this, we need to use our 70 divided by our 2, which is our growth rate, right? That's going to give us 35. Okay, so then we're going to do 2012 plus 35 equals 2047. And that's going to be our answer for this one. Okay, and then to get the next one, when it doubles again, we're just going to do 2047 plus 35 and get 2082. And that's going to be our answer for this line. Okay. Here's another one. A country's population was 12 million in 1992, and in 2012 it is 24 million. Okay. If the population grew at a constant rate, the percent growth was what? Okay. So in this one, we're going to do it a little differently. We're going to do 70 divided by R equals 2012 minus 1992. Okay, so then we'll have 70 divided by R equals 20. Okay, then we'll do, take that R, we'll move it to the other side. So then we'll have 70 equals 20R. And then we'll have 70 divided by 20 equals R. So we'll have R equals 3.5. Okay, and that's how you do that. So that's kind of 2 ways to do the growth rate formula. Oh man, now I need to define the following. Okay. The total fertility rate. Gosh, these are seem like something that is not super useful. Well, I mean, it's useful. It's just like a definition doesn't seem as useful as like doing some math or something. Estimate of the average number of, but I guess you do have some recall questions. A woman will have in her lifetime. Okay, the next one, let me move this over. Replacement level fertility is the number of children a couple must have to replace themselves. Which is, believe it or not, you think it would be 2, but it's actually a little over 2. Infant mortality rate, number of infants out of 1,000 who die before their first birthday. Well, that's sad. The crude birth rate is births per 1,000 people annually in a population. Deaths per 1,000 people. Why is this one so tiny? Let me write this again. Deaths per 1,000 people. Okay, that showed up. Okay, so now I'm going to draw a curve that gives you logistic growth, which is basically S curve, and then I'm going to label your carrying capacity so you can see it. Okay, so I'm going to try my best to be straight. It's going to look something like this. So that's going to be your logistic growth. And then your carrying capacity is basically going to be right here at that flat part. Your carrying capacity is known as K. And if I could, I would have made it like a little closer to this line, but it's basically like right there. Okay, we're math. In a particular year, the population has the following characteristics: a crude birth rate of 45, a death rate of 20, an immigration of 1, and that emigration is 5. They're basically pronounced the same way, but I like to say immigration and emigration. That way I know the difference. Like you can hear the difference, even though that's not really how they're pronounced. Okay, so the percent growth for that year is. So our formula for this is going to be crude births minus crude deaths divided by 1,000 equals R. Okay. So if the immigration rate is 1%, that's going to be 10. 10 is 1% of 1,000, and then the immigration, 5, is 0.5% of 1,000. So then we'll take, I'm going to draw this formula, and then I'll like hit enter so you guys can see it before I put the answer. Okay, so there's our formula. We have our 45 here, our birth rate, plus this 10, and then we have the 20 plus the 5, right? And so that's going to give us 3%. Okay, I don't know what makes all these text boxes here. It's kind of annoying. Okay, we may go a little bit over. If you have to leave, that's totally okay. This will be recorded, and you can just watch the recording later. So here we go. Let's draw the idealized demographic transition. Okay, so the birth rate, let's do this. It's going to be kind of like this. And then it's going to go down. And continue to go down. And let me draw these, the kind of sections of the demographic transition. You know, we have like phase 1, we have phase 2, 3, and then there's 4. So we'll call this 1. I like to write it like this. And 4. Okay, now I'm going to use a different color for the death rate. And so the death rate, basically, in the beginning, they're both high. The birth and death rate are high, right? Then what happens is the death rate starts to go down. Let me see. Low. Okay, and then the population. So basically, what happens is in a demographic transition, you're going to have a high birth and death rate initially, and then what happens is the death rate will start to go down, but the birth rate will kind of like lag behind a little bit. So you're, I should have drawn it like a little more up and then down. But anyway, the birth rate lags behind a little bit. So even though the death rate is lowered, the birth rate stays high for a while, and then slowly the birth rate comes down to kind of meet the death rate. So that's kind of what happens in the demographic transition. Now we want to label age structure diagrams that represent slow growth, rapid growth, negative growth, and zero population growth. Okay, so let's see what I can do. So an age structure diagram would be slow growth would kind of look, it could look like this. One that has rapid growth, you're going to have a really big lower area, and then it's going to get kind of really skinny. One that has negative growth, you're going to have not very many little folks, but you're going to have more older people. Then zero growth would just be like completely flat. Like it would be like the same. It'd be like a column. Okay. So those would be some age structure diagrams. It's the best I could draw anyway on the computer. Using the axes on the right, draw and label survivorship curves, exemplifying early loss, late loss, and constant loss species. Okay, so let's see what we can do. I'm going to use purple for early loss. So this is when you're going to have lots of babies die, but not so many old folks. So this would be like things like clams or corals. They release lots and lots and lots and lots of babies, and then not many of the babies survive, but then the ones that do, they survive for a long time. Constant loss would be like just a flat, like a straight line. Like I said, if you guys have to go at 7, that's totally fine. You can watch the recording later. And then late loss would be like they don't have very many babies. Lots of the babies they do have survive. Usually it's because they have a lot of parental care, and then they die when they get old. This is kind of what humans do usually. And so let's see what's going on this graph. This would be kind of like one of those data questions. Basically, this is showing that fertility rate goes down the more girls are enrolled in school. So this basically means like the more education you have, the less children you likely have. And this is because a lot of times women that are more educated can make decisions about when and how many children they want to have. And so they tend to have fewer. Okay, now match the most populous areas in the world with the respective continent. We are pretty close to being done. Mexico is not in Asia. It is in South America. New York City is in North America. Mumbai is in Africa. Jakarta is in Africa, I believe. I had these written and then they like jumbled them up. Sao Paulo, I believe that is in South America. Delhi is in India, which I think is considered Asia. Osaka is Asia, Shanghai is Asia, Tokyo is Asia, Seoul is Asia. Okay. Onward. Okay, our selected species. So when we looked at that survivorship curve that showed where lots of babies were dying at the beginning, those were our selected species. So they have lots of offspring and very low to no parental care. Okay, K-selected species have few offspring. These are usually what humans are. And they have lots of maternal care. Right? Usually your parents take care of you once you're like 18, sometimes longer. So those are K-selected species. Whew, this section is short. Okay, define the term biome. A region defined by inhabitants and climate. It's often the plants, right? It's often called by the plants, like a grassland or something like that. Okay. So what determines the type of biome an area will have, and that is your climate or your geography. Well, your geography determines your climate, and your climate determines your biome. Okay, so here we go. Here's a some biomes. There's not much left, I promise. These are in the tropics. Imagine that. The temperate deciduous rainforest is it's not still in my temperate zone, right? And the taiga is in like where it's cold. Okay, the climate is hot and wet. The time for a deciduous forest is they have seasons and mid-rainfall. So not too much, not too little, right? Cold. The taiga is very cold. Low rain. Okay, some common plants. You're going to have a dense canopy of plants. Right, you're going to have all sorts of stuff. High biodiversity. So I'm going to write that right here. Remember, your biodiversity is your variety of plants. You're going to have birds, all sorts of stuff. Birds, amphibians, mammals, insects, all sorts of things. Here, you're going to have deciduous trees. See what I was talking about in the last one, how it said, like, defined by the plant species. It's called a temperate deciduous forest that has deciduous trees. And this one, you're going to have deer, hawks, foxes, owls, that kind of stuff. In the taiga, you're going to have conifer trees, like needle trees, cone trees. And you're going to have things like moose, bears, stuff like that. Okay. These are kind of our last slides. The next one, a tropical grassland, where it's going to be in the tropics, right? The temperate is going to be in the temperate zone. Polar regions, near equator, the desert usually. Your tropical grassland is going to have hot and rainy and dry seasons. Okay, your temperate grassland is going to have seasons and usually moderate to low rainfall. Your tundra is going to be cold, low rain. And your desert is going to be hot and low rain. I'm going to write that big because you're going to have like very, very little rain. Okay, so now let's talk about plants. In your tropical grassland, you're going to have tall grasses. Some trees, not many. The animals you're going to have, this is like a savanna, right? So you're going to have a lion. I'm going to call it safari animals. In a temperate grassland, you're going to have short grass. And you're going to have stuff like small mammals, maybe things like buffalo, stuff like that. In the tundra, you're going to have short grasses, permafrost. That means the ground is stay frozen all year round. Polar bears, seals, stuff like that. In the desert, you're going to have some succulents. And then you're going to have like lizards, maybe some like rodents, stuff like that. Okay, a rectangular area of forest that measures 10,000 meters by 30,000 meters has an area of how many kilometers and square kilometers and hectares. So I'm going to go ahead and do that math for you. And I'm going to do it in, I'm going to write it like this. So this is 1,000. Hmm. 1,000 times your 300,000, then you're going to get 3 e to the 9 meters squared. I'm going to multiply that by 1 kilometer squared divided by 1 e to the 6 meters squared equals 3 e to the 3 kilometers squared. Okay, so that's your kilometers, and if you want to do hectares, you can do 3 e to 3 times 1. Let's do that 1 e to 4 meters squared equals 3 e to the 9. Okay, and this is the last slide. Okay, so this should be pretty easy. So this should go really quickly, and then we can be done. The Taiga could be like Russia or Canada. The desert could be like any of the countries in northern Africa. Tropical rainforest, you can have Brazil, Costa Rica also has a rainforest. A temperate grassland could be the USA. We have one. Tropical grassland could be like Congo, Nigeria, where you would take a safari. A temperate deciduous forest could be in the USA, France. Tundra could be in Russia. This is like, why is it